Welcome to the Geofabrics Academy session on geomembrane protection efficiency using cushion geotextiles. My name is Ryan Hackney and I am the Environmental Solutions Specialist here at Geofabrics. I've been involved with testing lining systems for protection efficiency for over 17 years with both European and Australian methodologies, and this session will provide an insight into the various aspects of these methods. A general overview of this session is given in the current slide, and we will start by briefly looking at a lining system in the waste and containment sector and the various elements within that system. It is typically a HDPE liner that we focus on in the system when we perform protection efficiency tests and limiting strain on this part of the system to ensure its long-term barrier function. Stress cracking, it's the Achilles heel of HDPE and the reason why we want to limit strain on these types of geomembranes. And we can limit strain by introducing a cushion geotextile into the system. So we will discuss the various types of cushions, as not all nonwovens are the same. A focus on this presentation will be on two protection efficiency methods, the European LFE2 or the ISO method, and the modified ASTM-D 5514 method that is routinely used here in Australia. There will be discussion on the various strain measurement techniques and a section on influencing factors on the strain response. And we will finish the session with a discussion on allowable strains prescribed in design of these systems. A waste containment lining system forms part of an engineered void into which waste materials are then placed. The lining system prevents the leachates generated from the waste stream polluting the surrounding environment. The systems were traditionally a thick layer of compacted clay, but as time has progressed, these systems have become more complex and introducing geosynthetic materials. There are now single line systems, double line systems, composite line systems, and double composite line systems, to name a few. But the topic of this presentation is a focus on the barrier and the cushion, or the protection component of this system. The lining system typically includes a subgrade at the base onto which various layers of geosynthetics are then placed. The system can include a GCL for secondary containment, geocomposite drains for groundwater pressure relief or for leachate collection, a HDPE membrane that serves as the barrier, and a cushion geotextile to protect that HDPE from the overlying drainage aggregate that is part of the leachate collection system. When this void is eventually filled with waste, the pressure of that overburden acts on the lining system, and the protection efficiency testing ensures that the system is replicated in the lab and the most appropriate cushion is utilized for limiting strain on the HDPE geomembrane. HDPE geomembranes are the most common geomembranes used in the world due to their high level of chemical resistance and their mechanical properties. A high-density polyethylene is categorized by its density, with that density being greater than 0.94 grams per cubic centimeter, or 940 kilograms per cubic meter. Anything lower than this value is classified as a low-density polyethylene. HDPE geomembranes are actually, in fact, a medium-density polyethylene resin, but it is the addition of the additive package, such as the carbon blacks or titanium dioxide, plus the stabilizers and antioxidants that increases that medium density past the 0.94 grams per cubic centimeter density boundary. Hence, the geomembrane is classified as a HDPE. HDPEs can have different surface finishes, including smooth, textured, or monotextured. HDPEs can also be monolithic or co-extruded. Co-extruded geomembranes can include different surface layers, including white and black extruded into one geomembrane liner, or it can include functions such as a conductive layer that can then allow the membrane to have a liner integrity survey carried out once the liner has been installed. The table on the right there, it indicates what effect density has on polyethylene geomembrane properties. So as the density increases, the crystallinity of the membrane increases, and it's the high level of crystallinity that gives HDPE its high level of chemical resistance and its high mechanical properties. The increase in density results in the increase in tensile strength, an increase in stiffness, as I say, an increase in chemical resistance and an increase in abrasion resistance. But in fact, that higher level of crystallinity can also give some detrimental effects to the liner. The impact strength can decrease, the stress crack resistance can decrease, the permeability can decrease, and also the processability decreases. So HDPE, it's susceptible to stress cracking. So one of the fundamental properties of HDPE is its stress crack resistance, and HDPE is susceptible to stress cracking due to its crystalline lattice structure. So the crystallinity of HDPE is between 40 and 60%, and we don't use true HDPE-based resins in geomembranes. This is because they have that high level of crystallinity, and therefore the stress crack resistance would be too low. So this is why those medium density polyethylenes are used, so that higher stress crack resistance can be achieved. And stress crack resistance, this is a limiting property of HDPE. So this is what determines the long-term mechanical durability and the resistance to mechanical damage from stresses. So that's during installation and welding. And stress cracking is a brittle fracture, and that occurs under a constant stress, and that stress is less than what the yield or the break strength of the material is. So while if a material is under an amount of stress lower than that yield point, over the long term, that the material can potentially have a brittle fracture, and the material can crack, and then you no longer have a impermeable liner in place there, because it's become brittle and cracked. So yeah, stress cracks, they occur after an extended loading at those low stresses, and it's due to the breakdown of those tie molecules in the polymer. There's a bit of a diagram on the right hand side there that depicts that. Those tie molecules, they're like tethers, and they pin together the laminae, and they're responsible for that ductile stress strain behavior of HDPE. And just to highlight stress crack resistance, it's not identical in all HDPE geomembranes either. So it's a function of the resin used, and I've said HDPE resin used there, but it's, you know, this MDP resin. The molecular weight of the resin, the molecular weight distribution, and the co-monomer used in the production of the HDPE, and that gives the manufacturer's product the desired mechanical durability. So a step on from stress cracking is environmental stress cracking, and that's different to stress cracking. Environmental stress cracking is actually an acceleration of stress cracking, and that's caused by when the membranes are exposed to detergents, oxidizing agents, and chlorinated solvents. So there's a distinction there between stress cracking and environmental stress cracking. So something to be aware of there. And stress cracking, it can be limited in HDPE, and it can be limited by selecting resins that have high stress crack resistance, and that's determined in accordance with an ASTM test method, ASTM D5397, and we have geomembranes on the market that can achieve in excess of 3,000, even 5,000 hours now. And just to highlight that GRI GM 13 specification on HDPE geomembranes, we can see that the stress crack resistance timeline has obviously evolved over time. So, you know, back in 1997, that specification for stress crack resistance for geomembranes was 200 hours. In 2003, that was upgraded to 300 hours. And in the latest upgrade in 2014, geomembranes, HDPE geomembranes now have to achieve greater than 500 hours. But as I say, there are membranes on the market that can be, you know, a factor of 10 greater than that minimum specification. So in terms of reducing the risk of stress cracking, precautions are taken to limit that stress and strain on the in-service HDPE. And HDPE geomembrane designs, that they're aimed to limit the local strains on the geomembrane, and they by also limiting strains, there's also a proportion of that that's achieved by utilizing cushion geotextiles. So cushion geotextile we saw in that cross section earlier, in that profile, it's placed interfacing the geomembrane, and it protects protects it from overlying or sometimes even underlying particles that can cause point loads on the membrane. And as I say, it's typically in a landfill scenario where you have a drainage aggregate layer plus an overburden stress that's acting on that, that's imposing the stresses on the liner, which lead to these strains that can potentially stress crack the material. So there are laboratory methods that are used to determine the most appropriate cushion geotextile and limit the strain on the geomembrane, which we will talk about in a few slides' time. So just slide on cushion geotextiles there as well. So cushion geotextiles, these tend to be heavier weight, non-woven needle punch geotextiles. They have mass, they have volume, they're thick, and they have that function to cushion, to have that space to cushion those aggregate particles and prevent them from imposing significant stress on the geomembrane. So within the non-woven needle punch geotextile category, you can then look at subcategories of these types of geotextiles as well. So there's obviously a range of polymers that we use in geotextile manufacture, but there's also different methodologies of manufacture as well. So I've listed 4 points there, and some examples are we can have a polyester continuous filament needle punch non-woven, such as Bidham. We can have polypropylene continuous filament needle punch non-wovens, and we can source them from Solmax. They have a TS range of geotextiles. We manufacture here in Australia polyester staple fiber needle punch non-wovens. That's the Texel R range of geotextiles. And again, we manufacture here in Australia, in Queensland, polypropylene staple fiber needle punch non-woven geotextiles, TexLP. And it's key to highlight, and you're going to see some examples of this, that even though all of these geotextiles are classed as non-woven needle punch geotextiles, because of that polymer type and because of the different fiber types, they behave quite differently in terms of cushioning performance, and you'll see some examples of this. So yeah, just to highlight, a 500 gram per square meter mass per unit area continuous filament polyester, it's not going to perform. They have different levels of performance compared to a 500 gram per square meter staple fiber polyester. The two different things, and as I say, I'll highlight that in later on in this presentation. Okay, so let's move on to the methods, and there are a number of methods available globally, but I'm going to focus on the two in this particular presentation that we see specified here in Australia, because yeah, we can talk about the others, but I think it's important to just focus on these in this particular presentation. The first of which is a methodology that's used in Europe, and it's called LFE2. It's from the UK Environment Agency. LFA2 is the Landfill Engineering Document 2. And this document is titled Cylinder Testing Geomembranes and Their Protective Materials. There's also an ISO equivalent of this. The ISO standard and the LFE standard. The ISO standard has a performance section at the end, and the two methods are pretty much aligned in terms of how the test is performed and how the strain is measured. So we talk about LFE2, but it also includes that ISO methodology as well. So the LFE2 methodology, it's adopted from a technique originally developed at the University of Hanover, and it has a pass-fail criteria within that methodology, and that pass-fail criteria is that the measured strain is less than or equal to 0.25% strain based on the maximum average local strain, and we'll see some examples of these calculations. The test should be conducted using the actual geomembrane that's going to be used on site, the geotextile, and the aggregate proposed. That's quite an important aspect. When we do these tests, these performance tests, we need to be testing with the site-specific materials. There's no point using any old geomembrane or geotextile with a certain mass or an aggregate you get from the local hardware store. It has to be the materials that you're going to use on site and that are specified. In terms of the geomembrane, there's a clause there in LFE2, and the clause is that experience has shown that testing textured geomembranes can cause problems during that strain measurement process. And for this reason, when a textured product is proposed, the test should actually be carried out using a smooth geomembrane of the same density and thickness and formulation from the same manufacturer and using the same manufacturing process. So whether that be blown film or extruded, it's important that when you're substituting a textured for a smooth to do the actual strain test on, that it's from that same manufacturer and same technique. And that recommendation, it crosses over to the other methodology that we'll talk about as well, the ASTM methodology that we use here in Australia. Because when we're measuring strain to these really fine levels, those textures can actually impinge on the recording plates that we use, and it can create some disturbance in terms of how we measure displacements and therefore calculate strain. So I think where possible, it's important to highlight if we can use a smooth geomembrane in this test, the guidance is there. We recommend to use a smooth membrane in the test. So the LFE2 test, the cylinder test as we call it, it differentiates between two types of strain: local strain, incremental strain, and average local strain. So local strain, that's expressed as the difference between the deformed length of a straight line between 2 points that we measure on the indentation on either side of the deformation, and the undeformed length between the two same points divided by the undeformed length. And you can see a depiction of that there on the right. You have this deformation, you have LU, which is the undeformed length, LD, which is the deformed length, and we calculate the strain by looking at the difference of one over the other. Incremental strain is, again, the same calculation, but it's a particular segment along that length. So when we want to measure this, full deformation length, we actually have to split it into 3 millimeter segments according to this methodology. And those 3 millimeter segments, you can see on that picture below the engineer's table there. Those 3 millimeter segments are split across the indentation. As you move across the indentation, the incremental strain is the amount of strain at each point across those 3 millimeter segments. When we measure an indentation according to LFE2, we pick a particular indentation and we draw an X and Y axis through that perpendicular to each other. And we measure the strain in 3 millimeter increments across that indentation. So the average local strain is the mean local strain of axis 1 and mean local strain of axis 2. The average of those is what we call the average local strain. Okay, so to set the test up itself, we use a cylinder, or the labs that perform the test use a cylinder, and within this cylinder we can load it up with the materials in question that are used for this protection efficiency test. You see a cross section of it there on the right. The cylinder has to be greater than 300 millimeters in diameter, and at the base of the load cell, you have at the base of the cylinder, you have 3 load cells that are recording the amount of load that you're applying during the test, so you can calculate the stress at the interface at the base of the test. And then on top of the load cells, we have a steel plate, and on top of that steel plate, we have a rubber pad. That rubber pad has a particular hardness. It has a shore hardness of 50 plus or minus 5, so a range between 45 and 55 shore hay hardness, and that's to replicate a subgrade. In terms of what type of subgrade that replicates, you know, it's quite a stiff rubber if you look at the shore hardness scale. But there are, and the rubber can degrade over time as well, but there are checks that are done on the rubber to ensure that the rubber falls within that shot hardness range as you're doing the test. You split the rubber up into 20mm sections, you measure the shot hardness in every one of those sections, and if the shot hardness is out of specification, you need to replace the rubber. So there is a level of control there in terms of that rubber and what the specification is of that. So on top of the rubber that's replicating that subgrade, that's when we start lining up the lining system. On top of the rubber, we place a 1.3mm lead sheet, and it's the 1.3mm lead sheet that's the recording plate. So once we apply load onto that lining system, it's the lead sheet on the underside of the geomembrane that's going to record the indentations. So the geomembrane then is placed on top of that lead sheet. Obviously, on top of the geomembrane, we place the cushion geotextile, and on top of the cushion geotextile, we place the drainage aggregate to a minimum of 150mm depth. And that aggregate's loose; it's not in a fixed profile. It's loose. It's poured from your container loosely into that cylinder, and then we use a layer of 50mm sand on the top of that, and that is really just to level off that surface so that you can evenly apply a load of a loading plate on top of the cylinder. So I hope that describes how the test is set up there in the cylinder. In terms of applying the stress or pressure for the test, the methodology, again, it outlines what that calculation should be. So the calculation is based on the depth of waste, the waste density, the acceleration due to gravity, plus a factor of safety according to the test temperature and the amount of time that you run that test for. So if the test is typically around for 100 hours in this case. Many of the tests that are run in Europe run this 100-hour test at 20 degrees Celsius. So the example of a calculation there at the bottom, if we've got a landfill with 20 meters waste depth, it's got a waste density of a ton per cubic meter. We're doing a 100-hour test. We can then apply that 2.5 times calculation factor, and we end up with a test pressure in this particular example of 490.5 kPa. So the method actually defines how you calculate and apply stress for the test. When it comes to the end of the test, after that 100-hour period, you release the stress and you carefully remove that lead sheet. This lead is quite easily deformable. Lead's quite a soft metal. It needs to be removed within a specific time frame at the end of the test, and actually the deformation measurements need to be made within a specific time as well, because the lead is soft. It could continue to deform once it's been removed out of the equipment. So what the operator has to do is select 5 indentations on that lead sheet, which visually they see as having the greatest deformation lengths, and it also has to take into account the depth and the steepness of the indentation slope. So you can see that example there of a lead sheet on the right there. It's a bit of a challenge for the operator, to be honest, and I've done many of these tests over the years. You've got to pick out of all of those indentations that you see on that lead sheet, 5 that the operator deems to, have that most deformation. So that's one area that you see where there can be some differences between laboratory measurements, because of it's very dependent on the operator and what they actually pick as those indentations, and it can get more difficult in terms of the level of indentations. If you've got a low stress and a geotextile that's well cushioning the material, the membrane, you can end up with these quite light indentations. You can see an example on the left picture there. You can actually see, if you look closely, you can see those crosses and those circles that are marking the indentations. That's where the deformation measurements have been taken. So a dial gauge crosses this and it scores the lead as it passes across. And so you can see you're measuring quite a small area in terms of strain of this this deformed lead sheet. And as I mentioned in previous slides, when we select these 5 indentations, we then have to go to each indentation one by one. We run a vertical vernier and horizontal vernier across the deepest and longest indentation in the let's call it the X direction, and then we find the deepest point, and then we run perpendicular to that in the Y direction and take vertical and horizontal measurements across that indentation at 3 millimeter increments. So 2 sets of measurements per indent, and then we take the average of those to measure that average strain. So we measure 5 indentations, but it's actually the 3 indentations with the highest mean strain values on both axes that are actually used as the final strain value. So while we measure 5, we only consider 3 of the worst in terms of what that strain measurement is and what the final mean strain reported is for that particular test. An example of the measurements here, you can see that we're moving 3 millimeter increments across. So if you look at this X box, indentation 1 X axis, in the X direction, we move across the indentation horizontally in 3 millimeter increments. So we go 3, 6, 9, 12, all the way up to 51. So this particular indentation is 51 millimeters in length. And at each one of those 3 millimeter increments, we measure the displacement, the vertical displacement with a dial gauge, and that's the XZ column there. So the XZ is how much the deformation goes into the lead. So we can then use these numbers to calculate incremental strain. So at each 3 millimeter point, you have these incremental strains that are calculated, and then the summation of the summation of X gives you the LU. So we've got a deformation, undefined deformation length of 51 millimeters. When we add up the LD, so we use Pythagoras by measuring the horizontal and the vertical. We then use Pythagoras to get the hypotenuse. The summation of the hypotenuse deformations gives us LD, which in this case is 51.133. And that by using that calculation I've given previously, we get to a local strain of that x-axis of 0.26%. We then do the same in the perpendicular y-axis direction. We again get a set of data with incremental strain, and the summation of those give us the local strain for that particular section. And then if we average both local strains for the y-axis and the x-axis, this is where we get the mean local strain for that indentation across those 2 axes. So we do that 5 times on 5 indentations, as I mentioned, and we pick the 3 highest mean local strains that then go into the report, and that's what is reported as the mean local strain. Hope that makes sense. Okay, moving on to the method we use here in Australia, because I'm not aware of any laboratory here in Australia that actually perform the LFE2 or the ISO methodology. The laboratories here are all set up to perform the ASTM D5514 modified methodology by Hornsey and Wishaw. So this gives you a depiction of the equipment that we use. It's rather than a large hollow cylinder, it's this cell that we use, this pneumatic cell. We're not using as much aggregate because we're just using a layer of aggregate that's set in a fixed rock profile, and the apparatus is set up so that we can either do inverted tests with the rock on the base and the lining system above, or we can have it in the normal orientated situation with some spacers so that we can include subgrade and GCL, lining material and rock on top. So there's a couple of ways we can do it in this apparatus, inverted or in a normal fashion. As I say, this test method, it evaluates the stress strain properties of the geosynthetic by using pneumatic pressure to compress the geosynthetic over a synthetic or a natural subbase. And we use a fixed rock profile, and that's made from the site-specific aggregates. These diagrams just give you a few of the different types of tests we do in this apparatus. This has sort of evolved over time. Traditionally, this methodology was a inverted test where we have the drainage aggregate on the base, the protection geotextile, followed by an aluminium sheet, which is that recording plate, and then the geomembrane, and then the stress is applied via air. So the geomembrane acts as like a bladder under that pneumatic stress and imposes the load on that system onto the aggregate. This is how the test has been traditionally done. It's sort of evolved over time, over the years. We can include GCL into this system as well, so we can look at the profile, including GCL and membrane. But again, more recently, we also include the full profile in this apparatus as well. So that includes subsoil, GCL, recording plate, membrane, cushion, aggregate, and then just a sacrificial bladder that's used to apply the pressure. So there are a number of ways of doing this test, and the designers specify this in their project specifications, what elements they want to see. There's a level of conservatism that can be used using this traditional inverted test, whereas if you want to be site-specific and really get to a low level of strain, you have to incorporate this full system in the test. So in this methodology, the proposed site aggregate is sent to the lab. Again, same as LFE2, it's very important that you're using the site-specific materials. This aggregate is then set in a resin or a grout, and that fixes the particles into position. And this is the main difference between the two European and methodology that they use here. It fixes those rock particles, and by fixing those rock particles in place, it allows for repeat testing, and it reduces that variability of the change in topography of the rocks. If we were to use loose rocks and we had to test various different cushion geotextiles at the same stress, you'd get that change in topography, and you're unsure whether you're actually assessing the change in what the change the geotextile makes, or if it's just the rocks that are influencing that as well. So we're reducing the variability in the test by fixing the rocks in this way. The procedure of setting the rocks in this rock profile, it ensures that the rocks don't fall flat. They're poured into a liquid silicon layer. That silicon layer then cures. The rocks behind that silicon layer are set in resin. And when everything is set, we then remove that silicon layer, and that exposes the topography, the valleys and the peaks of the rocks as they would fall in situ. As I mentioned, it's now common to include subgrade soil and GCL in the test, and it's just important that there's some specification around that. The soil needs to be compacted to site conditions, so optimum moisture content plus or minus a moisture percentage, and the dry density, the compaction criteria. It's important that we have those site-specific parameters, that we replicate that in the apparatus. Otherwise, we'll end up with a soil that's maybe softer or harder than what you have in situ, and that can influence the outcome of the strain as well. Same with the GCL. We can place the GCL in there dry. We can replace that in there to a hydrated level, whether that be 50%, 100%. We just have to have that instruction in terms of how the system is going to best replicate what's happening on site. As I mentioned, it's very important to use site-specific materials. The geomembrane proposed, we're going to decide on what the geotextile is. The rock, we do get asked if, we have a large database of these results, but that can give you an indication of where we need to start in terms of a cushion, but we need the actual site aggregate to do this test. There's a lot of variables in the aggregate itself that I'll talk about that influence the strain. So we need to be using site-specific materials. Very important. The test here, it's usually a 24-hour period. There's been research done in the past there. You can see that in the references, but the The test is typically run for a 24-hour period. It can be run longer, but as I say, the typical test period is 24 hours. And the aluminium sheet, we're using an aluminium sheet in this particular test methodology. It's a 0.3 mm aluminium sheet, and that's what's used to capture the deformations that are imposed on the geomembrane during this loading period. So at the end of the test, again, we recover that recording sheet. In this case, it's an 450 mm diameter plate. That aluminium plate then gets laser scanned with a set level of precision. The laser scanner is actually capturing those vertical deformations every square millimeter. So if this is a 450 mm diameter plate, there's about 160,000 measurements that are taken with that laser to record the deformation at every square millimeter. And then from that, we can do some calculations, which I'll talk about, that convert those deformations into strain. This just depicts the level of detail that the laser is capturing in terms of those deformations. So as I say, for every square millimeter, the laser is capturing how much the geomembrane has deformed. And moving on to the strain measurement. So from that 450 mm diameter sheet, the outer 50 mm is discarded to discard for edge effects, and we focus on that inner 350 mm, which equates to about 90,000 data points. And then in terms of measuring the strain, the software takes one of those square millimeter points and it measures the distance between each one of those 8 neighboring 1 mm squares. So one in each corner and one upper north, south, east, and west of the middle square. You can see an example on the bottom section here. So on the left, we've got the deformations in millimeters. We then apply this similar deformation strain measurement using these Pythagoras calculations to record the deformed length, and then we can get the strain at each one of those points around the surrounding square. So the software will measure the strain at each one of those points according to the deformations, and the square at which has the largest strain is then assigned to that middle square. And that process is repeated for all of those 96,000 millimeter squares. And you then get a topographic profile of strain that you can see on this heat map here. So you have the red areas where you have the high levels of strain, and the blue areas that have lower levels of strain according to this methodology. So we're picking up the strain in every square millimeter, assessing that on that resolution there. Not every 3 millimeters like you see in the LFE2 method, not just 5 select indentations. Every single part of that plate is captured on a 1 millimeter resolution, and the strains measured at every single point around it, not just x-axis and y-axis, every single point around it. So we get a really high resolution in terms of what the strain is. This again just depicts the level of detail that laser scanner picks up. So from that data that I had previously, these are just the deformations. So you can see this is obviously on an exaggerated vertical scale, but you can see the level of detail that the laser scanner is picking up, and we're measuring the strain across every single peak and trough there, not just 5 or 3 indentations that are picked by eye. So there's some significant differences there between the methodologies. Once the cells have been assigned that strain value from that measurement methodology, these are then categorized in terms of a percentage of the total area, and that they're categorized in strain ranges of 0.25% increments between 0 and 25%. This data is then presented in a cumulative form on a graph that you can see on the right, showing the percentage of area versus that cumulative strain, where 100% of the area represents 0 strain. So the limit of precision of this scanning methodology is reached at 0.05% area. So once you get past that point, if you do 10, 20, 30 repeat tests on the same profile, same textile, that's where you start to see the data start to vary. So we pick that limit of precision to determine the maximum strain. There's lots of factors that influence that strain response, as I mentioned earlier. So with the aggregate, there's the particle size distribution, there's the angularity or its roundness, the rock aspect ratio, so something that's a lot longer than it is in its width has an influence compared to something that's got a good 1-to-1 ratio. The geological provenance, so something that may split during the test, it might have a lot sharper edges, can influence. The membrane type, its thickness, its base resin, its profile, whether it's structured or not, the site conditions, the level of stress that we're imposing on the system, the temperature, whether the site's confined, the amount of time that we apply the stress, the subgrade type can influence, so the soil type, the compaction criteria, whether it's moist, whether it's dry, whether it's dense, whether it's less dense, the GCL, the grade of GCL, its level of hydration, and the process that we hydrate it under stress as well can impact how stiff that bentonite is. And then the geotextile, as I mentioned earlier, there's the polymer, the fiber type, the manufacturing method. So you look at all these different factors, there's a huge range of outcomes here. It's not as easy as just having a table and saying, okay, I've got a stress of 700 kPa and I've got a 20mm rock. I'll pick a 700-gram continuous filament. It doesn't work like that. It would be nice to be able to do that. We have a general idea because of the number of tests we've done over time and the number of rock profiles that we've produced, but it really needs this site-specific test on a job-per-job basis. In terms of some results, I'll briefly go through now. The effect of no geotextile versus geotextile. This just depicts that geotextiles reduce strain. The dotted line shows that we achieve 6.2% strain here without a geotextile under 200 kPa with this specific rock profile. If we introduce an A44, we can reduce that strain down to 4.5%. If we use a thicker geotextile, A64, we can reduce that down to nearer 3%. So this is just depicting geotextiles perform that cushioning function. They reduce strain. The geomembrane thickness, yes, given it is only a 24-hour test, there will be some changes over the longer period of time that the membrane's under stress, but over a 24-hour period, you can see that a 2mm geomembrane, which is the solid lines, compared to a 1.5mm geomembrane with the dotted lines, we measure some difference in strain between those different thickness geomembranes. The blue lines are being done under 400 kPa with a specific rock profile, whereas the green ones have been done with a different profile and a higher load, but it's really just showing the difference between 1 and 2mm geomembranes and the different level of strains that can be captured. The subgrade has an influence, as I've mentioned previously. So you've got 3 depictions here of no subgrade with the blue line, a softer subgrade with the pink line, and a hard subgrade with the green line. So by incorporating subgrade in this methodology, in this particular example, we go from a strain with no subgrade from to sort of 9.5% through to closer to 6% by including subgrade. So when we talk about not including subgrade in the test and doing the traditional methodology, this is why we know it's a conservative method, because you're applying that full pressure on the membrane. It's got no support. It's pushing into all those indentations. You record a higher level of strain. So if you want that inbuilt level of conservatism, factor of safety, we'll do the test with no subgrade. But if we get into very site specifics and really wanting to understand the performance of the full profile, we'll include the subgrade and again, the importance of conditioning it to the correct compaction criteria. Again, another example with subgrade, without subgrade, under a specific 470 kPa stress, without subgrade, 5.9% strain. By inclusion of that in the system, the strain, same textile, same pressure, same stone, but by including the subgrade, the strain is significantly reduced because it's supporting the geomembrane. The geomembrane can't deform as much without having that subgrade in place. Geotextile type. So in terms of the geotextile type, there, as I mentioned, we've done lots and lots of repeat testing with many different geotextiles. This data set shows one rock profile that's been tested with a range of geotextile masses, but also a range of different polymers and a range of different construction methodologies. So continuous, this data set encapsulates continuous filaments, staple fibers, polyesters, and polypropylenes. And you can see by that distribution that there's you know, a poor level of correlation there. So it's hard to deduce, you know, in terms of mass and its impact on what that has on strain. But if we split that up into the different geotextile types, blue continuous filament polyester, red continuous filament polypropylene, green staple fiber polypropylene, and purple staple fiber polyester, we get that really good level of correlation. And you can see there is some distinct differences between the different geotextile types. So as I say, this has all been tested at the same stress, the same rock profile, the same geomembrane, just those different data points and different geotextiles with different masses and different polymer makeup. So the example that you can see here is if you was just to specify an 800-gram mass per unit area geotextile, you're going to get a very different result depending on the polymer type. If you use a bidum, if you use a continuous filament polyester, you can see that we achieve a 6.5% strain. But if you was to use a staple fiber polypropylene, you're getting almost double the amount of strain for that same mass. So I guess the takeaway here is that it's not just to focus on mass. Staple fibers, continuous filaments, even the polymer types, they behave quite differently. You could look at it from the different aspect. If you needed to achieve less than 6% strain with this particular profile and load, you could maybe achieve that with an 850-gram continuous filament polyester bidum, but you're going to need probably 2,000 grams of staple fiber polypropylene in this case to achieve that same level of strain. So just highlighting here that all geotextiles are certainly not the same when it comes to a mass specification. The allowable strain. So hot topic. And really the allowable strain. You know, the measurement of strain. It's used as an indirect measure of the stress that exists in the geomembrane that might result in stress cracking. The objective of specifying these maximum allowable strain values is to limit the in-service stress to a subcritical value where stress cracking is not going to be a problem in practice. That's from this extract, this paper. I encourage you to read that by Ian Peggs, the allowable strain of geomembranes. There's a link there at the bottom. And just an extract there from Vic Bepham as well. It's important to draw the distinction between global strain and local strain. So a maximum strain of 0.25% global strain, which is at any location, is sometimes mistakenly specified for HDPEs, which is very difficult to achieve in practice. So you've seen that example that I've given you earlier of the LFA2 measurement methodology, where we're measuring those mean local strains, whereas in the ASTM methodology, we're actually measuring the maximum strain on that full plate. So that's assessing every single data point and measuring the strain across that full profile. And the end result is the maximum strain on that full profile that we've measured. So there's some recommendations given by Peggs, and it's also replicated in the Bepham guidelines. You can see there's actually a specification in terms of different resins. So low stress crack, high stress crack. Obviously, the higher stress crack resistance, it's less susceptible to stress cracking. So there's some relaxation there in terms of what the maximum allowable strain can be. This paper goes into a lot more detail in terms of the justification of these numbers for each one of those polymer types or profiles. So I don't have time to get into the specifics of that there, but it could be a topic for another session, or feel free to contact me and we can talk about it further. And there's further commentary that in that paper that I've got an extract here. There's a general feeling amongst design engineers that the 3% general strain and the 0.25% local strain limitations are too conservative, and the practical performance of lining systems in the USA, where heavy puncture protection geotextiles are not used, it appears to support that position because they don't observe any failures. Even when they're using the lighter geotextiles, they don't observe those stress cracking failures in situ. Recently we've been doing some testing, trying to achieve really low levels of maximum strain. An example's been under 700 kPa with a 20 mil aggregate, which isn't really that aggressive when you look at it in terms of point loads. We've looked at one layer of 2,000 gram geotextile, 2 layers of 2,000 gram geotextile, 3 layers of 2,000 gram geotextile, and also 2 layers of continuous filament. We need to be 6,000 grams per square meter of geotextile to achieve strains close to 0.25% strain. That's a huge, massive geotextile. And I guess when you get into these sorts of levels, it's probably going to be more economical to look at sand as a protection layer rather than geotextile. So it just highlights the fact, we have these allowable strain values that have been nominated. We've come to a bit of a divergence, I think. We're seeing specifications for lower and lower allowable strains. But on the other side, we have HDPE geomembranes that have higher and higher stress crack resistances. So we're getting membranes that are less susceptible to stress cracking. They've got really high 3,000, 5,000 hour plus stress crack resistance values. But again, we're wanting to limit strain on those, to limit stress cracking. It's just some food for thought, I think. So I'm just going to finish on that point there, and references are available on request. So thank you for your time today. I'm just having a look at a few of the questions that have come through, so thank you for sending those. The first question is, what would be the purpose for conducting an inverted ASTM-D modified test? So the inverted test, it's really just how the test equipment is set up, and it's really just about how that load, how that pressure is applied onto the system. So in an inverted test, you're actually using the in situ geomembrane as the bladder to apply the pressure onto the system. So you have the rock sitting on the bottom, which is supported by the base of the equipment, followed by the cushion and the recording plate and the geomembrane. So it's the same system, it's just upside down. It's not having any impact on the test as such. It's just how that equipment operates. You can do the test. It's a way of doing the test without that supportive subgrade, without including the subgrade. It's that conservative assessment without the subgrade in place. So as I say, the other way of doing that is to turn the profile around, use some spacers in the equipment where we can actually compact soil into the bottom and include the subgrade and set the system up as it would be in situ. There's just a few different ways that we can set that up in the apparatus, and it's all just around whether we include subgrade or not. So I hope that answers your question there. You mentioned, there's another question here saying, are there any new test methods that may be under consideration that would reduce the chance of operator error in identifying the deepest indentations in testing? So a number of years ago, I don't know, it's probably 8, 9, 10 years ago now, I was included in a round robin program. This was initiated in the UK. And I think there were 4 or 5 laboratories as part of that round robin exercise. And I'm not sure if the results were published, but from my perspective, I got to see the outcome of the results. And this is what highlights the operator error, because that LFE2 methodology is a visual assessment, and you have to pick 5 out of hundreds of deformations. It's quite hard to get away from that. And the result of that round robin was that there was some disagreement between the laboratories in terms of the measured strains, because of that that operator variance in picking indentations, and what they visually thought was the worst indentations. And you asked the question, are there any test methods that may be under consideration to reduce that chance of operator error? Well, that's what's been implemented here. That's what's been implemented with the modification of ASTM D5514. That laser scanning methodology removes that. You're not having to select 5 indentations. You're measuring the whole sheet. You're measuring everything. It's done by software. It's picking every square millimeter and measuring the strain on that. So maybe, I don't know, the LFA2 or the ISO methodology could stick to the cylinder test methodology with the loose rock, etc., and the lead and everything else, but it might be worth considering changing the measurement technique. So rather than using this engineer's table and measuring in 3 millimeter increments, use the laser scanning method. I guess that is one option. Okay, we've got a question here. What is structured HDPE referenced in the last slide on allowable strains? So with HDPE geomembranes, there are different ways in which texturing can be imposed on the liner. So as I mentioned, you can have smooth geomembranes and you can have textured geomembranes. And the texturing, different manufacturers, or the same manufacturers even, have different texturing methodologies. Those texturing methodologies can include what's referenced here as structured HDPE. And that means that the texturing is it's embedded into the geomembrane as it's being extruded. You have rollers that have indentations on there. The rollers compress the membrane, and the structuring of the HDPE, it's usually a spiked type profile, is embossed onto the geomembrane as it's extruded. So you have a core of membrane, and the texturing is it comes out of that core. It's a monolithic structure. So other types of texturing, you can have spray-on texturing, so you can have a smooth membrane, and as the membrane's being rolled out on the line, as it's coming out of the line, a polymer can be sprayed onto the membrane and stick onto the membrane, and that's called a spray type texturing. And then you can also have something called blown texturing. So nitrogen's used. So when the membrane's extruded, when it's still in its molten state, high pressure nitrogen is blasted into the surface, and that creates a texturing on the profile. So you can have this nitrogen. So you've got 3 sort of outcomes there. You've got a structured profile where it's embossed onto the membrane. You've got a spray on where the texturing is sprayed on with a different polymer, and then you've got this blown texturing. So they can result in different properties of the material as well. The tensile strengths, the tensile elongations can change according to those different texturing technologies. Okay. And I think we have run out of time for today's session today. So thank you everybody for attending. I hope you find it useful. Any questions that I haven't addressed, I will get in touch with you to answer those via email. If you do have any questions, please email me at r.hackney@geofabrics.com.au, and I hope you found today's sessions useful. So thank you very much, and I'll see you on another Academy session. Goodbye.